Okay, so small crowd today. I actually like that because people who want to come. I don't know. I love the system of filming the lectures, and then I don't have to explain it to people who aren't here. They can just watch the lecture again, and the people who want to come. And I hope you ask questions, and we just have a nice group. I really love doing it this way. Other teachers are saying, well, I want a full classroom. This is what they're telling me. They don't want to do what I'm doing. And I'm hoping for it to spread, because I know students like it, to have the lectures filmed. But the biggest stumbling block is everybody wants, the teachers for some reason, want a full house. And I say, well, why? What if it turns out they learn better when they're, at home? Some people learn better at home. Some people, don't you want the people who want to be there and not people just being there because they have to? And it's really, I don't know, I'm having a difficult time getting through. And I'm not, and even students say, well, it's a sign of respect. If I sit there in an empty classroom, that means, or half empty, that means people don't respect you. I say, what? Why? I mean, I hope they respect that I'm letting them learn however they want to learn. It's just, it's a funny kind of feeling that students, and it's this consensus somehow that if this sort of, the only thing I can attribute it to is some kind of respect for authority and for authoritarianism. That I'm here, the teachers, from the teacher's point of view, and these are people who, the last people in the world I think were authoritarian personalities, but they say that I want them to listen to me, what I tell them to do, the instructions, and I like the feeling of giving those instructions and seeing them listen to me. And the students somehow say the same thing, that I want an authority up there telling me. And for me, teaching's always been more of a dialogue. And I feel like I learn as much from students as students learn from me. So look, I was raised in the philosophical tradition, right? The dialogues, that was teaching. That's real teaching, when the student and the teacher interact. So I feel like the smaller the group and the people who actually want to be here in the dialogue, that's great. They're going to get that kind of teaching. But the people who want just instruction or just watching it later can get that. And it's the best of both worlds. So I'm racking my brain to figure out ways to convince others, but the best way, of course, and the way that I completely believe in, is research and doing a study. So that's what's going on right now in Stat 100, as I think I've told you. There's a study, and it's going to be in 200 too, starting next semester. I'm offering an online course for Stat 200 that's just going to be watching the lectures online. And you can sign up for either one. And look, anybody, I think this is the way all your classes should be. And if the online people want to come to class, of course they can come. And if you guys don't want to come to class, of course you don't have to. You can watch it online and just make a fluid system. And what I'm trying to figure out, obviously I can't just compare exam scores and evaluate, because there's going to be self-selection, right? That's Stat 100 in the nutshell, self-selection. So what I'm going to try to do is stratify on all the, already, like in Stat 100, I think I've told you this probably, that we've given 7 exams so far. And on every single exam, the online people have outscored the in-person. Well, that's no surprise, right? Because people who sign up for online are probably people who feel more comfortable with computers and feel more confident. So how do we tease out, how do we get rid of the confounders? Build the models one way, which is what we're doing, and hopefully we're going to make Stat, I've been wanting to make 200 part of this research, and I think I will next semester, and I think it'll be really cool. So we could do that. Basically we're going to stratify on what we think might be possible confounders. ACT scores, for one, right? If the people who sign up for online have higher ACT scores. So you have to compare likes to likes. And it's going to be a cool, if I get funded for it, I have a proposal in right now, it's going to be a cool research project that's going to both Stat 100 and 200 are going to research ourselves doing it. So that's the idea. And then maybe I could spread, it's not just what I believe or what somebody else believes. Oh, students learn better when they're listening to me or they don't. We'll have research on it, which is the only way to figure it out. So I'm kind of excited about that. But it's funny, I was just looking at this classroom and it doesn't bother me at all. Whereas anybody else would look at, the good teachers, especially the ones who get rated very highly, they look at this and they're upset by it. Whereas I'm not. I wish you guys would sit closer and talk. But it's like, these are the people who want to be here. I love it. Rather than the ones who are socializing with each other and clearly are looking for their iClicker stuff. And to me, this is great. So I just don't, maybe with the research, I'll be able to convince others. Because, we all have prejudices. We all have biases, right? And that's the whole point of statistics, to get over them. I could be completely wrong. I could find out that the online people are going to learn better if they're in class, right? And then maybe I'll force everyone to come to class. But I have to be convinced of it. Okay, so that's what's going on. All right, so now here's where, good news. Today, even with my little speech, 5-minute speech, we're going to finish up the non-parametric stats right here. So we've got, for the first time ever that I've been teaching this, only, 6 semesters, we have 2 days for review, which is really cool. And so I'm going to give you also the final from last semester. So you'll have that to review. And why I've delayed on this homework is I'm not sure how to, maybe I'll just still keep it split up like this and just release them both now, but you can do both of them, right? You'll be able to do both of them at the end of this class. So that's the deal. And I just have to post one more bonus R, and then we'll have a bonus survey. And people have been, okay, so you guys have the final when? Wednesday. So if you want to take it, or if it's really, if you'd really prefer to take it here, this day, I'll give you a sign-up sheet so you can, not just if you have 3 finals in a row, but if you have a very strong preference. Otherwise, just stay where you're at. But if you have a very strong preference, you can take it with this other section and vice versa. And I'll put a sign-up sheet for you. Okay, so any questions on end of the semester stuff? So you're going to be in great shape for the final because you're going to have an actual practice test and a bunch of review material. Okay, so let's go and see where we left off. All right, so let's do this again and write it down. All right, so we have these, so we saw the lowest is when we have all zeros here. So we add the U counts, we rearrange these scores. These are, and we rearrange these, and now we have 81. We just took these 15 scores and ordered them from our very smallest, 7, and then the next 8, right? So we have 88, 85, 81, 85, 88, 90, 92, 95, 96, and 100. So we have 1, 2, 3, 4, 5, 6, 7, 15. If we wanted to do the ranks, this would be 1, 2, 3, 4.5, 4.5, 6, 7, right? And 8 through 15 here. But we're just doing it, now we're doing the U counts because we want to use this table here. So the U counts are, we looked here, and here was the most extreme. We saw none of these people beat any of those. So every single one of their U counts is 0. And these are not zeros. These are all what? 7s. Okay, and so what we said was, do you see how you have 7 8s? You have 56 all on that side. All right, now, what are we going to do? Now we said we could just rearrange, and we thought, well, maybe we should just take the highest one and put it over there, and that would give us a 7. And that would give us an 8, and then we switched one more. So we switched 2 of them, and now we have 11, 60, 65, 70, 70, and we said we're going to trade our 2 highest for the highest and the lowest over here, highest and the lowest. So that's what we did, and it's not the only rearrangement to get 10 probably, it's just the first one somebody thought of here. And then what's remaining on the other side is what? We put the 75, we switched our 2 highest, so they get 75, 79, 81, 85, 88, 90, 1, 2, 3, 4, 5, 6, 2 more, 95, and our highest here is 96 now. And now we said, okay, now still all of these, 11 doesn't beat anybody here, 60 doesn't beat anybody, no, 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 but 81 does beat 2, and 100 beats all 8. So we said, okay, here we got, when we add all those up, our UA count is 10. And here we said, okay, 75 beats everybody but those 2. So this is 5. 79 beats everybody but those 2. 79, 75, this shouldn't be an 8, this should be an 85 here, right? 70, yeah. 85, 88, yeah. 1, 2, 3, 4. Which one did I miss? 75, 79, I saw 85, 88, 92. Little old 92 should be in here. So sorry. Thank you. Thank you. And so you see all of these, and there's 6 left, are going to beat, they're going to beat everybody except for 100. Does that make sense to everybody? 85 beats everybody except for 100. There's 1, 2, 3, 4, 5, 6. 88 beats everybody but 100. 90 beats everybody but 100. 92 beats everybody but 100. 95 beats everybody but 100. And 96 does too. And so now we said 6 times 6 is 36 plus 10 is 46. And you have to check that it adds up to 56 because the number of possible pairs, as we saw before, is NA times NB. So any division, any UA and UB score has to add up to the number in A times the number in B. Does this make sense to everybody? Okay, and there's other ways you could do it. This is just supposed to be fun and giving you experience playing around with things here. Questions so far? Okay, let's move on. So now, I said that a strong point of this Wilcoxon-Mann-Whitney rank sum test is that, that it compares the whole distribution and not just the means or the medians, right? This means that the 2 distributions can have the same mean or median, but different scores, different U scores or different rank sum scores, and they that would reject the null. So I said, okay, let's compare 2 distributions that are both symmetric around the mean, like 2 simple distributions that are both symmetric around the mean, like let's just say group. Let's just make a mean of 0, all right? And let's just do 3 numbers, make it super easy. Okay, uniform, just symmetric around the mean, right? And let's do another distribution, another 3 numbers that we'll compare it to, that have the same mean, that are also same mean of 0 and are symmetric around it. So why don't we just say, instead of 1, we'll just make it a little bit further out, 2 and -2. Okay, so these are 2 different distributions with the same mean, right? Same mean. Do they have the same rank sum? Do they have the same U statistic? And they do. here, so it doesn't distinguish. This test does not distinguish. The question is, should we try it and see? If we did the rank of A, what would we get? Let's call this group A and group B. So here's group A and here's group B. They have the same means. Does our test pick up on that they have a different distribution? This one has a more spread. Okay, so let's see. So if we were doing the rank sum, what would it be? We'll do the rank of A and the rank of B. Now the rank means you put what? All 6 numbers in a list, and this is the smallest. So this would have a rank of what? 1. What's the next smallest? This would have a rank of 2, right? These would both be, this would be 3 and 4, both be 3, so we'll just say 3.5 for both of them instead of 3 and 4. And then this is the next biggest, and this is the very biggest. So what is the rank? If you add those up, and you add these up, you'll get what? 7 plus 3.5 and 7 plus 3.5 because they're symmetrical around. So here we'll get the same rank, same U as well. You could do the U's. And so it won't distinguish between 2 different distributions that are symmetrical around the mean. With the UA, you could do the same thing, and UB. So you say, how many? 2. How many is 2 outscores just 2 bigger than 1? Yes, so it has, but is it bigger than this one? No and no. So its U count is 1. Excuse me, -1. I'm doing -1, not 2. Sorry, I'm doing the actual value. So we're doing -1. Is -1, what's its U count? Is -1 bigger than -2? Is it? Yeah. Is it bigger than 0? Is it bigger than 2? So it has a U count of 1. How about 0? What's its U count? Is it bigger than -2? Yes, that beats 1. It's tied here, so it gets a 1.5. And it doesn't, how about 1? 1 is bigger than -2, and it's bigger than 0, so it beats 2, doesn't beat that. So that's its U count. Let's do these. So -2, does it beat any, is it bigger than any of these? No. Is 0 bigger than any of these? Yes, it's bigger than -1, so that's a 1, and a tie here, so that's 1.5, and it's not bigger. That's its score. And finally, 2. 2 is bigger than all of them, so it has a score of 3. So their U count should be the same too. They should both be 4.5 and 4.5. And remember, it's how many pairwise comparisons are there? For each one of these, we're comparing it to 3 things. So that's 3 plus 3 plus 3, or 3 times 3, which is 9. These 2 do add up to 9. And these 2 should add up to the numbers between what? 1 and 6, which is what? 6 times 7 over 2, right? Our formula, which is 42 divided by 2 is 21, and that does add up to 21. So that worked. But the answer to this question is no. Would it detect? No. But now, let's just do it asymmetric around the mean, and you'll see that it will pick up on the difference. So let's look at this again. So we can have the same A. We'll do the same A. And we'll do -1, 0, and 1. But now let's make B different. All right. So what should I make B? Let's see. I'll make 2 of the numbers way up here. Let's say 2 and 3. I'm just picturing a number line here. 0, 1, 2, 3. And then to make it average out to 0, I'll have to have -5. So it'll be way down here. So there's going to be one number way weighted down here. Like if you're doing a number line, you can see it looks like this. It's not symmetric around the mean at all. The mean is right there. This one's way further down. Whereas these are symmetric around the mean. There's your mean. And these are just uniform there, and this has gaps. So this is asymmetric around the mean of 0. Okay, so let's look at this. And so if we look at the rank of A, what is it? The rank of A, we can do the same thing. Now we have what? This is 1, right? This is easy. The next one, 2, 3, 4, 5, and 6. So the rank of A is just 2 plus 3 plus 4, which is 9. And the rank of B is what? 1, 5, and 6. 1 plus 5 plus 6, which is 12. So you can see why they wouldn't, because when you make it uneven numbers like this, you put more numbers on this side, but this one further out, it's not going to, it doesn't care if this is -5 or -500, right? Okay, so now the next one would be UA and UB, and this is very easy to see too. So -5 is lower than everybody, gets a score of 0. And 2 and 3, what are they? They both beat everybody, so they both get scores of 3. So it's 6 here. Whereas these all just, this is very easy to see, they all just beat that one. So it's 1 plus 1 plus 1. So the point is what? That these Wilcoxon-Mann-Whitney tests, they don't detect differences in distributions that are symmetrical around the mean. Two distributions that have the same mean. They won't detect differences in distributions that are symmetrical around the mean. But they can, but they can detect differences, not all of them, but they can detect differences when distributions are asymmetric around the mean. So that's just sort of a quick, easy visual for you to remember. So now we're going to do another, any questions so far? Okay, so now we're going to do another test. It's so funny to me that no matter how small you make the classroom or how big, you'll have students sitting way up close and way in the back. I used to teach at Uni High School, and there was this teacher who was super unpopular, a math teacher. I used to teach math there. And at the time, all the kids went to the U of I for her Calc 2 class and her Calc 3 class as well. They taught all the way through Calc 3 at Uni High School. And they just either went to U of I or they started taking the Mathematica version. And so I remember walking by her classroom. There were exactly 2 students in the classroom. One pushed his, he was like a real apple polisher, pushed his desk right up to hers and was sitting like right like this, right next to her. And the other one was a slacker. I guess his parents couldn't afford for him to do the, to leave that teacher and take it at the U of I. He was in the very last. And every day it was the same thing. It was like a person sitting, 2 kids, one sitting right up here, and the other sitting in the very back row, like sort of half asleep. And this teacher, bless her, I mean, I liked her, but she wasn't the student's favorite, taught exactly the same as if she had a lecture of like a full class. Even though there were only 2 students, she just went through all the proofs, everything, just as if, in an incredibly formal way, as if there was like a full classroom. It was kind of hilarious. But I just see, what I am thinking about is I see people in the back squinting, but nobody moves up. And it's like your identity is you're a back row person or something. And maybe in all your classes, I should ask that question. Do you always sit in the back row or do you always sit in the front row? Because people just like are creatures of habit. And people sit in the same spot whether you have assigned seats or not. Pretty much the same area. Okay, so that's the idea. So now we're going to, that was just a break before our next chapter. And our next chapter is, let's see what we've done and where we're going today. So we finally finished this. This was probably the heart, just to give you the basic ideas. We're done with this one, the Wilcoxon-Mann-Whitney test. And it's, you have a rank sum or a U-stat. We're on page 141 here, just to show it's its parametric equivalent is the two-sample t-test. All right? Now, we're going to look at these two. And this, what if you have three groups? This is for comparing two groups. What if you have three or more groups? The non-parametric equivalent is called the Kruskal-Wallis test. And you're going to get approximate it with a chi-square statistic called the H-stat. And it's analogous to the parametric equivalent is ANOVA, which is either an F-test, or if you have a big sample size, you can use a chi-square test. And then finally, we're going to do the last one, which is we're going to look at a correlation coefficient. And for all of these, we're testing them against the strict null that there's no difference between the two groups. It means, same here for three or more groups, that they're all the same mean. And here is that there's the correlation coefficient is 0. That's the null. All right, so let's look at this. So the Spearman rank correlation coefficient is a non-parametric version. Whoops. Look at these. These are only one page long. So now we're here on chapter 42, which is exactly one page. And it's we're going to be comparing means of three or more groups. And it's just an extension of our WMW to three or more groups. And it's the non-parametric equivalent of ANOVA. Huge advantage of all these non-parametric tests is you don't have to make these assumptions about the underlying populations, the underlying populations that the distributions came from. That's why they're simple. All right, so what are we going to do here? We're going to do exactly the same thing. We're going to compare the three groups. We're going to combine them all into one ordered list. So here we have, let's say we have three versions of the final, okay? And I want to make sure that all three versions are equivalent, right? I don't want to give a harder final to one group than another group. So let's say I take a small group of students, pretend it was randomly distributed from the whole group. And here we have a group of 16 students, 5 in this group, 5 in this group, and 6 in this group. And I want to see whether I'm trying to see if these are of equal difficulty. Not only that the means are the same, but hopefully that these, I'd like to also do something a little bit stronger and say the distributions are the same as well. So they're, okay? So they're not easier for, it's not like, okay, the means might be the same, but I don't want it to be much easier for the really hard, bad students or the really good students or something like that for a particular group either. All right, so I combine them all into one ordered list, and I rank them from 1 to 16. And if there are any ties, like here's two 70s, so instead of saying 5 and 6, we just give them 5.5 here, okay? Same way we did before. There's nothing new here. We've just done the rankings, and we've just combined them into, we just have three groups, all right? That's step 2. So, and so this one has N1 here, N for group A is 5, and N for group B is also 5, and N for group C is 6. So they add up to 16. All right, now, why can't we just do a z-test? Because now we can't boil the difference down between 3 groups and just do a single signed number. We have the problem that we always have when we're trying to compare more than 2 groups. We can't just subtract the means because there's 3 of them now, right? So instead, we do what we always do when we have multiple groups, which is we square the differences. So we could look at the absolute value of the difference, because if you just look at the differences, they're going to sum to 0. So we square them, because we want to look at the magnitude of them. We could do the absolute value, but we generally don't do that in statistics. So for the same reason, we're going to do a chi-square test. So let's look at this. All right. So here we have these are their actual scores. So 10 was the lowest score, so it gets a rank of 1. 60 was the 4th lowest, etc. So we're going to change these to their ranks. So 160 is 4, 70 is 5.5, 80 is 8, and 100 is the highest one. So we're going to add those up, and the sum of those ranks is, what is the sum of these ranks? 34.5. Okay, and we'll do it for all of them. So 50 will be 3, 70 is 5.5 again, 81 is 9, 85 is 10, and 95 is 13. So we add those up, and I got 40.5. So that's the rank sum here. And finally, 20 was 2, 75 is 7, 86 is 11, 90 is 12, 98 is 14, and 99 is 15. And then I got the sum here is equal to 61. So I better check what? I better check that 34.5, what is 34.5 plus 40.5, right? So it's 75 plus 61 is 136. That's what it adds up to. And just to make sure I did it right, I want to check what? That the numbers from 1 to 16 add up to, remember, 1 plus 16, 2 plus 15. Another way to think about it is that this part, n plus 2, 1 over 2, is going to be the average. So 17 divided by 2 is going to be the average, which is, there's an even number here, so it'll be right between 8 and 9. So that is 8.5. And on the average, it's n, which is 16 times 8.5. So 16 times 17 over 2. This part's the average. This part right here is 8.5. So it's like having 16 8.5s. And that is 136, so it checks out. All right, and now the expected sum for each group would just be what? It would be the group number in the group, times the average. Right? The overall sum is just the total number. This is the total number. This right here is the total number. So it's the same formula, just applied to the group. Because remember, the groups were randomly chosen. So you'd expect the average, 8.5, in each group. So this one would be 8.5 times 8.5 right here. So you'd expect, these are the expected ranks. And right here is our observed ranks. So these are our observed ranks, and these are our expected. This one's the same thing. It's going to be 5 times 8.5. So this will be 42.5 as well. And this one is 6, because we have 6 elements in that, 6 numbers in there, times 8.5. So that is 51. So, okay, so there we have, these are our expecteds. So now we have this statistic here that follows a chi-square distribution, and the degrees of freedom is the number of groups, which is always minus 1, which is always the degrees of freedom for a chi-square. So we're going to have 2 degrees of freedom. All right, now this kind of looks like a chi-square distribution. You have the observed minus the expected squared, and it's usually over the expected, which is really over the expected variance. You know, it's the sum. Chi-square is the sum of basically normal distributions. So you have the observed minus, with our usual normal distribution, it's the observed value minus the expected value over the standard error. But when you square it, it's going to be observed minus the expected squared. And we have a sum of them, sum of these z's, observed minus expected squared, over, instead of the, when you square the standard error, it's the variance for each group, the expected variance. And it's distributed as a chi-squared. So now we get this 12 again. And some people ask me to show that after, show where this 12 came from. First of all, this looks very, very similar. Let me just show you. Let me just rewrite this. So we have this H stat. And by the way, you can tune out now if you want to just take a break, because this, if you just care about what's going to be on the exam, because this will be given to you. No need to memorize this formula. This will be given to you. No need to memorize. So it doesn't, unless you're interested, you can look here. And you can see that basically if you put this part down in the denominator, we're going to get the standard error that I showed you before, this with the same 12, that 12 down there. We'll get that. So you can see that that's just simplified. So you could write it as, we could write this as the sum for all the groups from I is equal to 1 to 3. Well, we'll just say to G for the number of groups, right? And then we have what? The observed rank sum for each group, R sub I, minus the expected for each group, R sub I, and that's squared. And then here we have what? I'm just going to make it look exactly like what we had before. I'll just make sure it looks like that, like this. So I'll have under the square root sign the n plus 1 over 12, plus then I'll have the, it's very, very similar to that, right? So let's do that. So it's going to look like, if I stick this under there and square it, wouldn't it look like you'd have the square root of, you'd have this little n1, right? N sub I, then you'd have your n times n plus 1 over 12, and then you'd have this thing squared. So it's basically the same thing. But people, where does that 12 come from? It doesn't matter how big, how many numbers you sign. It's always going to be 12. Do you know where that comes from? Do you want to see that? Does anybody want to see that now? Raise your hand if you'd like to. Okay, we can just do this. It won't take long, but you can still sleep if you're not interested. All right, so let's just look from where we found that, where we first did that, and that was right here. So this is also going to be given to you. So let's write that here so you don't have to memorize this. This will be given, so you don't have to memorize it on the final. But now let's see how we would come up with that. All right. So, all right. So you know that, okay, so this is a standard error. Think of it as, let's just compute it as a variance. So if we squared this, what is think of a standard error or a standard deviation squared. Basically, I'm going to do the standard deviation squared of numbers between 0 and n. And that's where this 12 comes from, and then change it to a standard error. So if we take the standard deviation squared, that's going to be the sum from I equals 0 to capital N. So if you went the numbers between 0 and 10 or 0 and 100, whatever, you know that you take your deviations and subtract off the average, right? Those are the deviations, and we sum them all up. We just sum them all up without squaring, you get 0. So you squared them, and then you divide by n. And take the square root if you want to do the standard deviation. That's just our formula for standard deviation. All right, so now you can simplify that and just break it up into two parts, and you can say, okay, you have the sum from I equals 0 to n of x sub I squared over n, and this is just algebra, minus x bar squared. And that's a formula, the computational formula that a lot of people learn for the standard deviation. So now, what are we going to do? Now, what I'm going to do is just, let's say, the easiest way to see this is if you just took the integral of this between 0 and n, and that's where you could see that the 12 comes, where the 12 comes from. So if we just took the integral, right, from 0 to n of x squared over n, and then this is just this constant. If you add up the numbers between 0 and n, like between 0 and 10, what's the middle number? What's the mean? It's just going to be n over 2, right? 0 and 10, 5's the middle number, right? If you did it between 0 and 100, 50 is the middle number. It's just n over 2. So this is just minus n over 2, and then it's squared, right? That's all that is. And so now I'm just going to integrate this. So when you integrate x squared over n, you're going to get x cubed over 3n, and you're just going to evaluate it between 0 and n. And this is just what? N squared over 4, right? So that's what you have there. And so now, what will you get? Put an n in for x, and you get n cubed over 3n. So simplify that, and you get n cubed over 3n. So you have n squared over 3. And you put a 0 in for x, and you get 0, minus n squared over 4. And find your common denominator, and ta-da, there's your 12. That 12 pops up all the time when you're looking at the integral of numbers between 0 and n. I mean the variance. Okay? So that's the idea there. And so this part is your standard deviation squared. And now, when you take the square root of that, of course, the SD is going to be the square root of n over 12. And that is what you're going to be, what you're seeing here, with some tweaks, because what we're doing is we're looking at the standard error of a sum of two groups, and these groups are dependent. When one's numbers, like when one's small, the other one's going to be big, etc. So it's tweaked a little bit, but that's the idea. That's where that comes from, that 12. And the square root of n over 12. Okay, so that's the idea. And we're not going from 0 to n, we're going from 1, so you get the n plus 1. It's just a little corrections on that. So that's finished. Now come back, everyone, and we're just going to compute this statistic. All right, so let's look at this. And so we're on page 139 now. And this you do need to know. So I'll give you this. I'm going to give you this. And now we'll just compute it. So what is age? Age is just going to be 12. You have 16 times 17. Now this is going to be the sum of what? We only have 3 groups. We have 3 sums. And what are we doing here? Let's just look at this. We're just taking this difference between, just want to go out a little. Can you see this? Okay. So look, we expect these. This sum, and this sum. But we've got these 3. So I'm just looking at the difference between, we'd expect 34.5, but we got 42.5. And now we square it, right? And divided by, this is an easy formula, divided by 5, because that's the group size. Okay, so we're going to have 3. The next one's going to be divided by 5, and the next one's going to be divided by 6. And each one's going to be the observed minus the expected. So this next one is still 42.5 expected, but here our observed is 40.5, correct? And here our observed was 61 minus 51. Does everybody understand how to just calculate that? All right, so what do we have now? So now we're just going to have 12 over 16 times 17. And I just want to show you, it's good to just do these differences in here just to check your work. So you get minus 8 squared over 5 plus 40 minus 42 minus 2 squared over 5 plus 61 minus 51 is 10 squared over 6. The reason I just want you to do that is just as I keep saying, these differences, before you square them, are going to observe minus expected. These deviations from the average are going to add up to 0. That's why you either have to do something, you have to get rid of that sign. So I just want you to check it to make sure you didn't make a careless mistake. So negative 8 plus negative 2 is negative 10 plus 10 is 0. So just make sure you didn't make a mistake along the way, because they have to add up to 0 before you square them. All right? But then once I computed it, once you did this, I got 1.344. So what are we going to do with that? That's a chi-squared with 2 degrees of freedom. So we're going to compare it to what? We're going to compare this, compare our statistic to what? To the critical value of chi-squared. I'll put a little star there, critical value at degrees of freedom equal 2. And we can compare it at alpha equals 0.05, which I know by heart because we've done it so much, which is 5.99. You don't need to know it by heart, but let's look. We've looked at, for some reason, we always end up with these 3 groups, or often we do the simplest is 3 groups, and then we have 2 degrees of freedom, and the convention is 5%, so there it is, 5.99. That comes up all the time. We see that. So that means what? So let's just write that. So here there's our critical. So we say 1.344. We're comparing this to that. We're comparing it, and we say 1.344, our statistic, is less than 5.99. So what? So we don't reject the null. Basically, do you remember like these chi-square statistics? Okay, so it's always going to be positive chi-squared. And with 2 degrees of freedom, remember it's really asymmetrical, so it looks kind of like this. Doesn't start looking right. And so this critical value would be like, that's 5.99. That's chi-square critical value right there. That's supposed to be a little star. 5.99. And what this means at alpha equals, this means that that when the null is true, the likelihood that you would see this big a difference. Look what we're doing, observed minus expected. We'd expect, if we got right on the button, we'd get 0, right? But that would be unlikely. So observed minus expected, observed minus. If you get really big differences, you get you're going to get a big difference, and you're going to get, even when the null is true, 5% of the time, that's areas, 5%, you're going to see this big chi-square statistic just by the luck of the draw. So our statistic wasn't, we're just going to say, okay, that's our cutoff. Just because people think less than 5% of the time, okay, we'll reject that and say that it's unlikely to be due to chance, because we'd only see it 5% of the time. But ours was what? 1.3 was way up here. 1.344. So that's going to happen a lot by chance. In fact, I looked up this. If you look this up on our p-value calculator, you get a p-value of 51%. So our p-value is certainly is certainly greater than 5%. How much greater? Our p-value is equal to 51%. So just by the luck of the draw, when the null is true, we're going to see this more than half the time. So of course we're going to say, okay, this is great. Go ahead, Ellen, give those finals. That difference is not significant. Does that make sense to everyone? I don't want to reject the null. I'd have to write new finals then. So that's the idea. And it's approximately distributed as this. All right, last thing, super easy. Again, this is the Spearman rank order correlation coefficient. And what are we going to be doing here? It's the non-parametric version of our regular correlation coefficient, R. It's abbreviated R with a little s, subscript s. Right there, see the little subscript. All right, and it's computed just like all correlation coefficients are. What we do, though, is we replace all the x and y values with their ranks. So if we have 7 pairs here, imagine 7 pairs, okay? And we want to compute, usually to compute a correlation coefficient, we'd look at the correlation between the x and y's, the actual values. But what we're going to do is we're going to replace the 7 x values with the ranks between 1 and 7 and the 7 y values. So all the numbers, the x, I just ordered them here between 1 and 7, and these will be in some other order, depending on, is that the lowest one? Let's do it. So this is let's just look at the x's. All right, this has a rank of 1 because it's the lowest. You see, I ordered them from, I just put the points that way. So this is 2, this is 3, this is 4, 5, and the biggest x value is there. So there's our 7x value, 7 points. Now, look at the y's separately and rank them from 1 to 7. Is that the strongest correlation coefficient would be if we also had the lowest y associated with the lowest x and the highest y associated with the highest x, but they're not. 45 is not the lowest y. 40 is. So this is 1. This is the second lowest, right? 40, 45. And our next, where's number 3? What do we have? Is that 61 is the third lowest. Then after 61, we have 70. And after 70, what do we have left? These 3 numbers. So that is the 5th, the 6th, and that's the top one, 99. So those are our pairs. So do you see why it's so much easier? It's very easy to figure out averages and standard deviations of these numbers and to compute correlation coefficients, and the distribution is very well defined because with 7 points, you're always going to have the numbers between 1 and 7. So the perfect correlation would just one matching up with 1, or perfect negative would be 1 matching up with 7, etc. So let's see what we've got here. So we've got 1, 2, 2, 1, 3, 4, 4, 3, 5, 7, 6, 5, and 7, 6. And now we're just going to compute our correlation coefficient the same way. What's our average? X bar and Y bar are going to have the same average because they're the same numbers, just scrambled. And you can see it's the middle number here would be 4. And that's 4. And the standard deviations for X and Y are also going to be the same. And I happen to know they're 2. It's very easy to see if you forget this. You can just see that what? Do you want me to, you know how to do a standard deviation. I don't have to calculate it for you, right? Raise your hand if you want me to quickly calculate and show you how to get it to. Anybody? Does anybody want to see it? 0 people want to see it. Okay. So what are we going to do here? A z-score. So remember our z-score is what? Z-scores are going to be just our value. These are just a list of numbers. So you don't have to worry about observed value minus expected error over standard error. No, it's just value minus our average. So it's over what? The standard deviation. So it's x minus x bar over your standard deviation. So here you're going to have 1 minus the average over 2. So it's going to be negative 3/2. What's this going to be? 2 minus 2. 2 minus 4. 2 minus 4 over 2. So it's negative 1. This is 1 below. 1 below, and you're dividing by the standard deviation of 2. So that's negative 1/2. This is right at the average, so it's 0. This is 1 above. So it would be, this would be 1, 2, and 3 above. Those are our deviations, 1, 2, and 3, right? But now we're dividing by this. So that's 1/2. That's 1. And there we get 3/2. Okay? So there are deviations right there. Negative 3, negative 1, negative. So these should all add up to what? 0. These should sum to 0. The deviations sum to 0. So when you divide them all by the standard deviation, they have to sum to 0. And they do. 3/2 and negative 3/2. 1 and negative 1, 1/2 and negative 1/2 and 0. All right, now let's do the same thing here. 2. 2 is 2 below 4, so it's 2 below, so that's negative 2. And then you're going to divide it by 2, so that's negative 1. 1 is negative 3 divided by 2. And 4 is right here at 0. This is going to be negative 1/2. This is 3 above, so it's 3/2. This is 1 above, and 2 above is 1. And make sure that these sum to 0. Negative 1/2, yep. Yep, they do. So these sum to 0 both. This has to sum to 0, and that has to sum to 0. So now what is the correlation coefficient? The correlation coefficient, R, is the product, the sum of the product divided by however many you have, the average of the products. So the average of the products of the z-scores, so we'll do that. So here the product of the z-score is negative 1/2, negative 3/2 times negative 1. So this is 1, negative times a negative is a positive. This is also 1.5. This is 0, 0. This is what? 3/4. This is 0.5, and this is 1. All right, so we're going to add all those up. That's 3, 4, 5 1/4. That's wrong, right? Yeah. Okay, so that's 5.75, right? 5.75 over 7. Okay, so this one is, that's why. Because it's 5 1/4, right? This is 1.5, yeah. See, there's no way to check this. They're not, I can't just add them up and get a, so just be careful. What did I do? I said 3/2 times 1 is 1. It's not. All right, so 5.75 over 7 is 0.84. Now, you'd think that was a really big R, right? Wouldn't you think that was really big, and so we could just reject the null for sure? But we only have 7 points. So let's just see. All right, for 7 or more pairs, we can usually look at exact probability tables, just the same way we did with the U-stat, and they're available. But for 7 or more pairs, the distribution of R under the null is approximately normal. All right, approximately normal. So the null is, so we've got 0.84, right? But the null is that it's the expected is 0. We're testing, that's the null hypothesis right here. That we get this, but we're testing to see how likely it is to get this high a correlation coefficient when the population correlation coefficient, we chose these 7 points from some larger population, is actually 0. Or how likely would a random distribution, if you randomly paired up 1, 2, 3, 4, 5, 6, and 7 with 1, 2, 3, 4, 5, 6, and 7, just randomly did that, right? You'd expect no correlation, but how likely is it to get a correlation of 0.84? So that would be if you actually looked at all those combinations, you could figure out the exact probability distribution. You could look at all the permutations, figure out each one, and that's what they have tables for. But with a big enough 7 or more, it's pretty close to the normal distribution. So we're looking at that difference. Like here's your R, and here's your z-score. You know what the z looks like. And here's your R. And you just want to know 0.84, how far out it is. I mean, you know that it can't, this is just an approximation, because this goes on forever, and of course the biggest the correlation coefficient can be 1. But so we're just doing an approximation. We're not caring about the big tails. We're just looking at, okay, for the 5% cutoff, we can get a good approximation. Obviously, this is cut off between 1 and -1. But I'm just doing we're doing it, people approximate it this way. And then over the standard error for R, which we usually know is what? It's easier formula than usual because we know the SDs. So we usually divide by n-2 because we're estimating an SD, but here we know them. So it's just, so people just divide by n-1. The usual, this is instead of, remember our usual one? Instead of, what's the usual? SE for R. It's the square root of 1 minus R squared over the square root of n-2. So this is much easier. I'm not going to give you this. You just subtract off -1. And now, when the null is true, this is 0. So the difference is that that's now. We were much more careful before because we weren't just looking for this strict cutoff like this. So it's 1 over n-1. All right? So that's going to be 1 over the square root of what? 6. And so I did this, and I got 2.05. So you say between 2.05 and negative 2.05. And if you look it up in the back of the book, you get 96% in the middle, which means, so this is where 0.85 is an R matches up. And so if you're doing this two-sided Z, two-sided alternative, then we're going to add both of those together, and our p-value is what? At 5%, if we're doing the 5%. This wouldn't be a good test if you really cared about, wanted to measure p-values way, way out in the tail, because this is cut off, the R, between 1 and -1, and conclude what? Conclude that there's very strong evidence